Hello everyone, welcome to this online course on material science. I believe this is lecture 10 in the module 1 on magnetism. If you recall, in the last lecture we started talking about the atomic diamagnetism in terms of quantum mechanical model, right? And we said that to observe diamagnetic effect in an atom, the atom should have a closed shell electronic structure, right? What that means, for example, we have the noble gases, right? Helium, neon, argon, krypton, and xenon. So all these noble gases has field shell electronic structure, right? So for example, if you recall from your first year chemistry, I believe the neon has electronic structure 1s2, 2s2, then 2p6, right? And the outermost shell is this 2. So for this neon we have n is equal to 2 and it obeys, we have 8 electrons in the outermost shell and it obeys this 2n square, right? The 2n square law. So that's the meaning of the closed shell structure. Also we have some alkali halides where, for example, sodium chloride, right? If you look at for sodium, it has 11 electrons, but the sodium ion inside sodium chloride has 10. So it's like a neon, like so closed shell structure. And also for chlorine, usually the chlorine as an element has 17 electron, but in the chloride ion it has 18. So in the third shell, it has a required number of electrons, right? And also, for example, in molecules like nitrogen, has 7 electrons. So if we look at the electronic structure, 1s2, then 2s2 and 2p3, right? So we have 5 in the outer shell, but we need another 3. So usually another nitrogen atom share these 3 electrons and then the outer shell becomes closed, right? So in this closed shell structure, the atom shows diamagnetic behavior, and I told you that usually diamagnetism exists in all sorts of atoms, but there are other magnetic effects which kind of overwhelms the diamagnetism. That's why to observe diamagnetism you need to consider an atom with closed shell structure, right? So now let's consider the basic concepts to understand diamagnetism in a quantum mechanical framework, right? Let's start with the discussion of magnetic fields then. So we need to apply a magnetic field, right, to calculate or to measure this diamagnetic susceptibility, right? We know that. We have discussed this in previous lectures. So our magnetic field, our model is a vector, right? Magnetic field is a vector quantity, and in three-dimensional space it should have 3 components, right? And the magnetic field we are using in this model points in the z direction, right? So in Cartesian coordinate, assuming that we have 3 unit vector I, j and k along the 3 x, y, z axis, this can be written also as b times k, right? So the magnitude is b and direction is along k. Note that I'm not putting any hat usually used in the vector calculus to denote the unit vectors, because it can confuse you with the operators in quantum mechanics, right? So when I write ijk, it means that they are unit vectors. That's one important thing. Another important thing I want to mention here, that magnetic field is a measurable quantity, right? And we are applying a magnetic field from some external source, like a magnet or something. This magnetic field does not depend on time, right? And does not depend on space also. So our assumption is this b is a constant, some constant value, right? It does not depend on space or time. Then the question is, the magnitude is b, right? The vector b, is it an operator? As I have mentioned in the previous lecture, that in quantum mechanics the measurable quantities usually represented by operators, right? The answer is that in this model our magnetic field is just a vector, not an operator, right? So this is a like a classical electromagnetism, right, where B is a vector. But the question one may ask that why we are not considering the magnetic field as an operator, right? The answer is we don't need it here. But then the question is there some other situation where this is required? The answer is yes. There are some advanced formalism when for example, consider the electromagnetic interaction with the matter, then the radiation field or the electromagnetic field has magnetic field in it, right? So there we need the quantization. So and then we can represent the magnetic field with an operator, right? So those are advanced formalism. But in this discussion, for us, B is just a vector, not an operator, right? And it points along z direction, okay? The number 2 point is that let's set up some coordinate to discuss our problem, right? So we are setting up some x, y, z. Let's say this is x direction, this is y, and this is z. This is the center of origin, and then we can specify any point in three-dimensional space with some position vector, right? Let's say we have a bunch of electrons, one of which is at location somewhere here and it's moving, for example. So we need to attach a unit. You need to attach a unit, position vector with it, right? To describe this position. And we know in quantum mechanics, this position vector will be elevated to an operator, right? So that's our position vector operator. And our magnetic field is pointing along some z direction, like in this direction. So B is pointing along this direction. Okay. Now, the next thing we need to discuss here, let's say point number 3, that what is our magnetic vector potential, right? So in the previous lecture, we have seen usually the magnetic vector potential is denoted by A in classical electrodynamics, and in general this could be a function of space r and time t, right? But in our case we don't care about this time. Our problem is time independent, so the magnetic vector potential is only a function of r. That's classical concept, right? Now this quantity will be elevated to an operator, right? So if I put a hat on top of some hat on the a vector, it means magnetic vector potential operator, right? But you have to understand this quantity is becoming an operator because the vector itself depends on the operator r, right? That's why this becomes an operator. Sometimes you will see, and this is very important, that in quantum mechanics books, no one bothers to put the hats anymore, because once you're experienced enough, you understand these are operators, and putting hat is kind of cumbersome, right? So that's why as we go along, we will use less and less hats on the top of the symbols. That's for convenience, right? So our vector potential is usually in this form. Then let us ask another question. What is this form of the vector potential? Now let me make a comment. You have certain degree of freedom to choose your magnetic vector potential, right? But you have to choose in such a way that the Maxwell's equation, which is very fundamental, holds, right? So that's our aim. In this problem of diamagnetic behavior of a material or an atom, right, we will set our magnetic vector potential, which is AR hat. Let's be pedantic for some time, and we are writing down everything explicitly. We will assume this has the form of half magnetic field cross product with the position vector. The question is, how do you know that? We have to check whether this holds or not, right? But at this moment, let's assume this is our vector potential, right? Can we evaluate its value? Sure, because we know how to evaluate the cross product, right? We need the I, J, and K, and then 3 components of the vector B, that's 0, 0, and B, and 3 components of the vector R. Let me put the hat here to denote that's an operator, right? What are the 3 components? That's x hat, y hat, z hat. In textbook, you will see there is no hat, right? But you understand those are operators anyway. Now, how do you calculate this quantity? Let me write it explicitly. The ith component should be this time minus this, right? 0 times z is 0 minus b times y. So let me write it this way: y hat times b. And we have an overall factor of half. So let me put it somewhere here. That's one. That's ith component. Then the jth component, minus is the convention, you know. For jth component, we need to do 0 times z time minus x times b. So we have minus x operator times the vector, magnetic field B. So this simplifies to minus by by 2 plus the jth component is bx by 2, right? Note one thing, that I am interchanging the b and x. So x is an operator, b is just a magnetic value, right? You can interchange them, no problem. And we will see the problem of interchanging variables come when there are operators, right? And we have discussed in previous lectures, it's the problem with the commutation. We will encounter this soon, but here this can be done. You can interchange any operator with some constant, right, which is the vector b. So this is our value of vector potential A. The x component is minus by by 2 and the y component is bx by 2, right? Okay. And y and x are vector operator. Now we need to check whether this value indeed satisfy the condition of the Maxwell's equation, right? And the Maxwell's equation that I need here is the one with the divergence of magnetic field is equal to 0, right? That's the famous magnetic field in Maxwell's equation, and one of the four. And also this implies that any time we have mentioned a vector quantity of which divergence is 0, that vector quantity must be expressible in terms of some curl, right? And we say that curl of a vector is usually the magnetic vector potential. So in our problem, this should be an operator, right? But as I've said before, even if I don't put the hat, you understand that's an operator. Okay, now let us find out the value of curl of A. We know what is the magnetic field in our problem, right? In our problem, this is B times K. K is the unit vector along the axis. Let's check whether the right hand side produces the same result. Then we know our assumption about the A is correct, right? So let's calculate this value. How do we calculate this? We need the ijk of 3 unit vectors, then the differential operator here, which is the gradient operator. So we have ddx, then we have ddy, then we have ddz. And for A, we have just derived this part, right? We don't have any k component, because you can see when you evaluate the k, it's 0 times y minus x times 0, so it's that 0, right? So let me put it here, by by 2 and bx by 2, all of them are operators, and also 0 here, right? Because there is no z component of the vector potential. Now the question arrives here that how do you calculate the same? Let me evaluate this value. So the ith component, so I'm considering this, so ddy times 0, which is 0, minus ddz times of bx by 2. Okay, that's 1. Then minus of z component, so ddx times 0, that's 0, minus ddz of by, right? ddz of by. And then the kth component. For the kth component, we have ddx of bx by 2. So we have ddx of bx by 2 minus, and then another minus here. So it would be a plus ddy of by 2, right? Okay. So let's see what we have here. So we are differentiating with respect to z. The b is a constant, right? And x does not depend on z. So this quantity is definitely 0. Here we are differentiating with respect to z, and we are differentiating the y, right? The y is independent of z. So this one is also 0. The only term exists is this term. So b is the constant, and if you differentiate x, that's 1. Here b is also a constant. If you differentiate y, that's 1, right? So the result is k, which is the unit vector. So let's not put any hat here. Unit vector k times b by 2 plus b by 2, right? So which is kb. So and on our, we know this is should be bk, right, or kb. It doesn't matter the order, right? So that's why it is shown here that our choice of the vector potential half b cross r is the right one, because it satisfies the Maxwell's condition, and indeed this is some magnetic field along the z, right? Okay, the next important point I want to make is, let's say that's number, what's the number should be? It should be, I said, don't worry about the number too much. Maybe I start now, right? So the next important quantity, which I have already mentioned at some point before, it's the angular momentum of the electrons, right? So in the diamagnetic atom, right, we have number of electrons, and we are saying that every electron will have some angular momentum because it's moving in the space, right? So the electron index is I, that's the ith angular momentum, and we know that's a vector quantity, right? That's why what we need to put here is Li vector and then operator. From classical physics, we know the definition of angular momentum is the position vector cross product with the momentum. So this is ith electron, so we need to put some index for the electrons too, right? And we know in quantum mechanics both of them are operators. That's how we define angular momentum operator for the electron. So that's the angular momentum for operator for the ith electron. So if somebody asks you what is the total angular momentum, you just need to add up all these angular momentums, right? Usually I runs from 1 to number of electrons. That's z. There are z numbers of electrons here in the atom. Now we need to add up all the individual angular momentum of the electrons, right? That's how you get the angular momentum operator. And next important thing I will discuss here is the kinetic energy of the electron, right? So kinetic energy of the electron, which is usually denoted by the T letter, and for the ith electron that should be an I, right? So this is the kinetic energy of the ith electron. I am putting some hat to denote this is an operator. In classical physics, forget the hat for a moment. The momentum, the kinetic energy is nothing but the momentum square divided by twice m, right? Mass of the electron. And we need to put some I to denote that's the momentum of the ith electron. I'm not putting any index for the mass because every electron are identical, the same mass, so we don't care about putting an index. But we need to put some hat because we are in quantum mechanical framework, right? So that's our kinetic energy operator. But I have mentioned before, right, in one of the lectures that if you want to understand the magnetic effect, you need to replace our momentum with the canonical one. Do you remember that, right? That lecture. You can review it if you want. So that's called canonical momentum. What is the idea of the canonical momentum? How do you get to the canonical momentum? The answer is that it's simple, right? All you need to do that whenever you see some pi, some operator regarding the momentum operator, you need to replace this by pi minus the charge of the object you are considering times the magnetic vector potential. And let me put the hat just to denote that this is an operator. That's how we convert some ordinary momentum to the canonical one. So in our problem of diamagnetic discussion, you understand the electrons have a charge, right? And the charge is in convention minus E. So for us, the canonical momentum is minus q minus e, so that should be E times A. So that's very important part. This is usually, if you have some, I don't know, maybe at some point you will learn these things. This is called the minimum coupling term, that you have to replace the momentum by P plus EA, right? Take this as a rule and you will see the consequence later. And as you go along in future, you will understand different angles or different perspective of this statement. That's our important canonical momentum, right? So once we have until this, in the next lecture, I will kind of continue in this line of thoughts, and we will see how to model the diamagnetic Hamiltonian to describe the atomic diamagnetism, right? And before I end, just to mention that we have the same three references that I have mentioned before, one from the Stephen Blundell, one from the Stephen Simon, and always the classic one, the Ashcroft and Marmin, right? I think that's about it, and thanks for listening.